I don't know how first.
I had to use it, but then like post that and I was like, I'm gonna do that. I'm gonna try to use it after. It's just so complicated.
Because somebody in the lab a few years before I got in the lab used Bayesian statistics to look at the distribution around. So you go in and you calculate the day that plants flower.
Yeah.
But you can sample that every 3 to 5 days, but it's not going to set primary when you're sampling them. So you can use this Bayesian distribution, but you come up with this distribution based on the data you figure out when it was most likely that the sampling was done. Or something. It's so complicated.
But like, yes. It's a cool way to do it.
That was a good discussion. Something that I'm always tempted to ask, and since we used up the time, I didn't sort of propose it. But the idea, sensible thing, seems to be that if you fail to reject the null hypothesis, you should compute a confidence interval. It tells you, basically, puts bounds on the extent of your knowledge about the thing you're trying to measure. And, if it's wide, then the correct answer is I have no idea. And if it's narrow, at least you can say I have some idea. But also, the point is often raised that even if you do reject the null hypothesis, you should also compute a confidence interval to again put bounds on the magnitudes. And so the question that occurs to me is, why do we do the p-value step in the first place? Why don't we just go straight to the confidence interval? Why do we test hypotheses at all? Don't we care about magnitudes? Isn't that what, anyway?
So why do we? Can we just leave it out?
Yeah, I don't know. It's become it's like a ticket to the banquet. Gets you in the door, but this is a topic that will come up again. Trust me. Okay, today I'm going to talk about linear models, and here's an outline. And a lot of the meat of the course is going to be about linear models or variations of linear models. And pretty much every test or parameter estimate that you've ever carried out probably involved a linear model or some variation of it. And so I thought it would be a good place to start to define exactly what a linear model is. And it's also the way that R organizes its analyses, and we'll be referring repeatedly to the basic structure of a linear model or something like that. So here it is. What is a linear model? Well, I'm going to tell you. It's any relationship between variables that looks like this. It has a response variable y. It has one or more explanatory variables, x1, x2. And then it has an error term as well. So any instance in which you can fit response data and attempt to fit it to explanatory variables, plus or minus error, you are fitting a linear model. And the betas that I've drawn here are the parameters of the linear model. It's simple as that. And here are a bunch of examples, and they represent, to a large extent, pretty much all of the analyses you've ever done that assume normal distribution of errors. So simply estimating a mean involves fitting a model to data. Or carrying out linear regression, that's probably the most obvious. When I said linear model, maybe the first thing that occurred to you was linear regression, and it's true. Simple linear regression is an example of a linear model. Multiple regression, where you have more than one explanatory variable, also a linear model. Quadratic regression, though, also has the same form, where one of the explanatory variables is x, and the second one is x squared. It's still linear in the parameters. It still has the same sort of structure, and so it too is a linear model. All polynomial regression is also a linear model. And what I want to show you here is that single factor analysis of variance is also a linear model and can be written in this form, and I'll show you that a little bit later on. So, just because, by the definition of a linear model, this is a linear model, but it doesn't necessarily describe a straight line. So, as I said, any polynomial regression would be curvilinear, the relationship between x and y, but it conforms to the structure of a linear model and can be analyzed in exactly the same framework. So it doesn't necessarily mean straight line. It's linear in the parameters. Linear models that you probably used go by all kinds of names. I've already said some of the examples, and here I list even more. But fitting a mean involves taking a model that this group has a mean, which is different from, say, 0, involves fitting a model to data, and that's kind of the culture of R as well. When you analyze data, you don't just estimate a mean; you actually fit the model to the data, and the estimate is something that you get out of that exercise. The same with linear regression, multiple regression. Fitting different means to two groups is a linear model, and single factor ANOVA is multiple groups. Multi-factor ANOVA, same thing. Analysis of covariance, just another linear model. They can all be written in this form. So that's why it's so general. And in R, there's really one sort of framework for analyzing all of those kinds of data sets, and the function R is called LM. So it's the command that you would use for fitting linear models of all kinds. So big deal. Why do we care that all of these different methods that had multiple names are all essentially just special cases of linear models? Well, common set of tools is one good reason for recognizing that they are all linear models. And in the case of linear models packages, they're often very flexible, and they allow you to, once you recognize that it's just a linear model, you can handle designs and other kinds of analyses that you may not yet have a name for. Built-in tools to estimate parameters, the sizes of the effects, which I have said earlier is what I think of as the biological significance of a result rather than the statistical significance, the magnitudes. LM is certainly easy to use. There are other linear models packages and other stats programs as well, like SAS. And this doesn't happen anymore because everybody has computers, but once upon a time there were like formulas for calculating the quantities in ANOVA tables. And that's all been replaced, and it's partly because those ANOVA tables couldn't handle unbalanced designs very well. So I'm going to start fairly basic to give you an example of a linear model, get you to sort of recognize some of its features, and then I'll extend it a little bit to talk about other kinds of linear models and how to interpret them. So this is a data set where some researchers sort of went out into the field with stuffed specimens of different raptors and introduced them to wild chickadees. I probably needed an animal care permit to do this. And what they recorded was the responses of the birds. And one of the things they recorded was the number of D notes per call. So, chickadee, you all heard them, you all recognize them. You probably thought they were just talking nonsense. But actually, there's information in the number of D notes per call, according to this project. And what they did specifically when they chose their raptors was that they took like gigantic raptors that would have no interest whatsoever in consuming a chickadee, not worth it, compared with smaller raptors that would easily find a chickadee-sized bird to be a tasty meal. And so what they did was they compared the number of Ds per call against the predator body mass. The idea being that these are low-risk predators and these are high-risk predators. And look at that. So count the Ds next time you encounter a flock of chickadees and determine whether you are dangerous or not. That's the magnitude effect. So how would we normally fit such data? How would we normally fit a model to such data? Well, linear regression is a very common tool used to fit such data. We imagine that the relationship fits, more or less a straight line. And the formula for that line is shown here. I'm assuming you're all totally familiar with it. Here's the response variable, here's the predictor, explanatory variable. Beta naught is the intercept of the line, and beta 1 is the slope. You may have learned them as alpha and beta, but I'm going to just call them different betas, because when there's more complicated models, that works better. When we analyze such data on a computer, we usually specify it in terms of a word statement. And that's how we sort of tell the computer what the model looks like that we would like to fit. And in the case of R, we don't have to include the intercept that's going to be there by default. So really, we just have to tell R that we're fitting Ds with mass. And the formula would look like this in an LM statement. So Ds squiggle mass. So that means that's sort of a word statement of the model we're trying to fit. And in this case, these are actually the names of the variables in the data set that you're asking R to model. So here we go. The way this works in R is, again, as I said, LM, and then we also include the formula. So that's something that we're going to do on Thursday. And what we're also going to do is we're going to shunt the results from this analysis into an object, an LM object that I'm going to just call Z or Z, I think. So again, there's the betas represent the ideal line that's out there, but now we're B naught and B1, those are the estimates that we get from fitting a straight line to the data. And the way R works is that once you have your model object here, you can use functions that extract information from that model object. And what I want to get you doing, and to sort of fix this as a habit, is that when you fit a model to data, there are kind of two things that you might want to do. And one is to estimate, and the other is to test. And so I want to encourage you to use summary to estimate, forget about the test results, and then we'll use ANOVA to test. Okay. And the reason for this is that although it works in single factor regression, you start running into trouble with this part of the summary table with more complicated models and with other methods that extend from linear models. So ignore everything to the right of the standard error when you use summary. And this is what a summary table would look like. There's your estimate of the intercept, there's your estimate of the slope, there's the straight line, and you also obtain standard errors for those estimates, give you an idea of the uncertainty associated with them. Predator body mass. Now what I want you to do is to show you a little bit about what R does kind of behind the scenes when you ask it to fit Y with X. And what R does is, so here's here's a column, that's your response variable y. And here's a column, that's your data on mass, and there's a one-to-one correspondence. You know, there's your first observation, its mass, and so on. What R also does is it creates this dummy variable of ones. And what that means is that in a compact sort of matrix formula, you can describe all of the y observations as the product of the intercept times 1 plus the slope times mass. So the first value for d's would be 3.95 is beta naught times 1 plus beta 1 plus 1.07, and then there's a residual associated with that. And so this describes every data point in terms of the two parameter estimates. Okay. The reason for the dummy will become even more clear later on, the need for it. Okay, so what R basically does, what any package would do, is that it seeks values of beta naught, or sorry, of B naught and B1 that minimize the sum of squared residuals. So here are all the residuals for a given B0 and B1, and you square them, you sum them, and then you search for the B1s and the B0s that minimize that sum. Okay, that's what least squares is all about. Why they call it least squares, because you're minimizing the sum of squared residuals. And so each of the residuals is the distance between each data point and the line. Each data, so sort of imagine those little vertical lines connecting these dots to the line, and this line, you know, what R is trying to do is find that line that minimizes the sum of squares of those residuals. And that's it. That's the least squares estimate of the regression. The linear regression. Okay. Now, you might not think so anymore after today's discussion, but what you might want to do is also produce a test of a null hypothesis. In this case, that the slope is 0. It would be hard to publish this result otherwise. Whether it's a good idea, well, we'll continue to have that discussion through the course. So use summary to estimate, use ANOVA to test hypotheses. Okay? So again, we've already done this and stored the results in this model object, and now we just extract the ANOVA table with this ANOVA command. And the table looks like this. And the p-value in the table is a test of the null hypothesis. The slope is 0. Okay, so you're all familiar with the row for the variable that you're fitting, the residuals, the sums of squares, the mean squares, the F statistic, and so on. So what I want to tell you a little bit further is that when R and general linear models, programs in general, test something like the significance of the slope, it's always doing something called model comparison. A test of any null hypothesis involves a comparison between two models fitted to the data. And one of those models is called the reduced model, and one of them is called the full model. And the reduced model is always the full model minus one or more of the terms contained therein. Okay, and you'll see the phrase referred to, and I'll refer to it again later in the course, is that the reduced model is always nested within the full model. So when you carry out an F-test, what R does behind the scenes is that it actually fits two models. Z0 and Z1, we'll call it. Z1 is the one that you thought you were fitting, and did indeed fit, and that is the linear regression with the formula here. But what R is also doing when it tests for the effective mass is it compares how much better this model is compared to the reduced model, which lacks the term mass. And in this case, what R does is it's just fitting a mean to the response variable, in this case d's. So it's essentially, the full model is your linear regression. The reduced model is a linear regression with a slope forced to be 0. That's the null model. And R actually fits that one too, behind the scenes, as well as the model of interest. And then the ANOVA command, you know, you can pass it just one model object, but what ANOVA does is it allows you to compare both model objects, and it produces a table that looks like this. the reduced model, the full model, and you can do this yourself. I did this. This was my result. And what the result told me is that the residual sum of squares from fitting the reduced model was this. And then when mass was added to the model, the residual sum of squares dropped to this value. And I fitted only one variable with a single degree of freedom used. And that's the sum of squares now associated with the full model and the F statistic. And what R does basically is ask whether F is large enough, whether whether the F ratio associated with including mass is sufficiently large to reject the null hypothesis that the slope is 0. Okay, so it's always making the comparison, and F measures the magnitude of the improvement in fit resulting from the full model compared with the reduced model. I do have a graph. So there's a visualization of the reduced model, there's a visualization of the full model, and R basically compares the improvement in the residual sums of squares and uses the F statistic to evaluate whether the fit is sufficiently better that we can reject the null hypothesis of slope of 0.
So the RSS of the reduced model is always lower than,
It's always
or higher,
lower.
higher than the
Yeah. This is always, the reduced model is always at a worse fit than a model. The more parameters you have, the fit always gets better. And the real question is whether the fit is substantially better, enough for you to say, yes, the slope is not 0. Okay. Here's another example, and this is similar to the first, except now there are more explanatory variables. And this is a data set on ant species richness in bogs and forests in New England. And I think all I used was the forest plots, and there's just 22. It's not a very large sample size, so the wisdom of fitting a multiple regression to such a small data set is suspect, but I have my disclaimer here that I'm just doing this for the purposes of this exercise. But you've been warned. Do as I say, not as I do. So what we would like to do is to see to what extent we can use latitude and elevation to predict the number of species present, the number of ant species present. And so, well, there's a problem with the distribution of species, so we're going to fit the log of species. That's our response variable. And so we're going to fit a multiple regression now because we have multiple x variables, the intercept, the slope for latitude, the slope for elevation, and then the slope, the coefficient associated with the interaction between those two. Here's a scatter plot of the data. The 3D plots, I don't know, they don't do a lot for me. But there you have it. Sometimes I think maybe if it moved, it would actually be better. I don't know, we talked about that a little bit, whether moving graphs can be an improvement over stationary graphs in the first lecture, in the graphics lecture. So what does R do behind the scenes? Well, it does exactly the same as I showed you for univariate regression. It creates a dummy variable, which is nothing but ones, and what that means is that it can write in sort of compact matrix form the relationship between the explanatory variables, the coefficients, and the response variables. So 1.8 log species is modeled as an estimate of the intercept times 1, the slope for latitude times its latitude, the slope for elevation times its elevation, plus the product of those two things multiplied by B3 plus a residual. And once again, R goes through and searches for the B's that minimize their residual sum of squares. And the way to get R to actually do that for you is to write down the equation as a formula in a word statement. And this is a compact way of writing of the word statement latitude plus elevation plus the product of latitude and elevation, the interaction. I just couldn't fit it all on one line, so I went with the compact version. That's a quick way to include all the interactions. And then we use summary, remember, summary to estimate. I've even knocked off the p-values here. And we get the estimates here for each of the terms in the model. The estimates are, take on these values here. There's the estimate for the intercept, and then the slopes for latitude and elevation. And so what is the interpretation of the latitude and elevation coefficients in a multiple regression? All right, so let's say here I am at the origin, 0, 0. And the latitude increases this way, and elevation increases this way. And the relationship between those two is like a plane fitted to all those data as shown here. And then the coefficients, what the coefficients mean is that log number of species decreases by 0.2369 for every unit I move in this direction, every unit of latitude in this direction. So not in that direction, but in this direction, latitude only. And the same is true for elevation. So the coefficient for elevation, it's pretty small, but it basically means that with every increase in elevation, the log number of species declines by that amount. So that's what the coefficients mean. And those coefficients then describe this fit here, which is practically a plane because the coefficient for the interaction is essentially 0. Okay, another linear model, in this case, multiple regression. Not too much of a difference from simple univariate regression. There are all kinds of other hazards associated with this that I'm not going to be able to get into, like when these variables are strongly correlated and stuff like that. If you ever do multiple regression, you'll have to dig into all of those issues. But I'm not going to go into them here. As before, use ANOVA to test hypotheses. So again, there's the equation. Here is the terms that were in the model, latitude, elevation, the interaction between the two. And then there are residuals, and here's the f-statistics and the p-values. So as I said before, in this case, as in the case of simple linear regression, R tests all of these terms by comparing two models. The full model and a reduced model that does not include that term. Now what I want to discuss with you is what exactly is that reduced model when there's multiple variables. It turns out that SAS and R do it completely differently. If you don't tell ANOVA, if you don't give it the reduced model and the full model that you want to compare, R starts churning away at its own program of action. And that program of action was decided by the creators of R, who thought this was best for you. Okay? And what that means is, in the case of R, is that by default, ANOVA will test all model terms sequentially. And in SAS terminology, that's called type 1 sums of squares. SAS itself, by default, uses type 3 sums of squares, and I'll explain to you the difference shortly. But what that means is that the order in which the terms are specified in your model determines the sequence in which those terms are tested. So order of your formula actually influences the result that you get. Most methods sections of papers that use LM in R do not mention this or how they decided on the order of terms in the model. But it should be said. R also respects hierarchy, and what that means is it always fits simpler models before more complicated terms. So it always tests the intercept first. Try as I might, I have tried to break LM to test the intercept after testing, like reverse the order of the intercept and the term. It won't do it, just won't let me do it. And then it tests main effects, which is relevant in ANOVA, and also here because there are interactions. And I have tried to break LM into testing an interaction without the main terms in there by putting it first in the model. It ignores me, or already knows that that's not good for me, and that the interactions should be tested after the main effects. R will never test an interaction between two terms like latitude and elevation without latitude and elevation also in the model. And that's actually a good idea.
How significant are the differences? If we
I'm gonna show you what it is for this case here. Okay, sequential testing means that order of terms in the model matters. And so I've written down here the sequence of model comparisons that R carries out. Well, you were wise enough to put latitude first. That must mean you think latitude is the natural first variable to enter to be tested in the model. And what R does is it fits a full model that contains latitude and intercept, and then a reduced model that includes only the intercept. Terms that enter the model later are not even considered. Next, when it tests elevation, the full model includes latitude and elevation. The reduced model and the intercept. The reduced model includes the intercept and latitude only, but not the interaction, because that comes later in the sequence. Finally, test